All right, next review, modeling data. Remember, this is when we're talking about bivariate data, when we have list 1 and list 2, and we're going to create scatter plots. First thing we want to remember about scatter plots when we're describing them, SOX is out, but we do have another way of describing them. Remember, we want to talk about the strength in terms of strong, moderate, or weak, and I'll remind you in just a minute. We want direction, is it a positive or negative? And then we want to determine whether or not it's linear or not. We don't have to say quadratic, it looks cubic, it looks something else. We just need to say, hey, that's linear, that's not linear. We don't need to go into any more details. So strength, remember, so a strong linear relationship, you're going to get a good, solid pattern. Um, doesn't have to have all the data points on the same line, but it's very apparent that we're going in a positive or negative direction. Moderate, it's going to be a little bit more scattered, but you can obviously still see the direction um, as we go through. Right, we can see that's a negative, but it's a little bit more scattered out. And then weak's going to be something that's going to be really tough to see. You might start to be able to see, it looks like maybe there's a general direction one way or the other, but it'd be really hard to make a strong determination. So one of the big pieces of data that we're going to pull from scatter plots and from these relationships is the least squares regression line of best fit, if you will. And remember, we use a plus bx, where a is the y-intercept and b is the slope. Remember, we use the linear regression. We're going to use a plus bx, which is a little bit further down the stat calculate menu. We're going to go a little bit further down. One thing to remember is every least squares regression line passes through x bar comma y bar, and really that's just the mean of list 1 and the mean of list 2. So x bar is the mean of list 1, y bar is the mean of list 2. All right. Interpretations for some of this stuff. First off, the slope. So for each increase in x, y increases or decreases by the actual value that is the slope, that number. Right? So it'll increase if it's a positive, it'll decrease if it's negative. The y-intercept, the interpretation, so that's when x is 0, the y is whatever the y-intercept. Keep in mind, a lot of these don't even have a practical meaning, but we still want to be able to interpret it. The coefficient of determination, remember, that's r squared. That's whatever that is, blank percent of the variation in y is explained by x. This is a good time to remind you that y sometimes is referred to as the response variable and x the explanatory variable. Right, so shocking development here that the explanatory variable does the explaining. As we start kind of picking through this stuff, we can talk about residuals. And basically, a residual is just going to be the distance a value is from the least squares regression line. All right, so if you do have some scatter plot, right, so here's our data points, and then if we were to plot the least squares regression line, a residual is just going to be that gap right there. So recall that a residual, if you're going to have to actually find a numerical value, you take your observed value and you're going to subtract from that the predicted value, and you get that predicted value, recall, from plugging into the least squares regression equation. So we can create a residual plot. Recall that you get that after a list. The residual list is created by the calculator when you run linreg. So since if that's been run, you get this residuals, and then you're going to plot list 1 versus list 3, and you get your residual plot. Recall that a good residual plot should be scattered with no pattern. You shouldn't see any outliers, right? Nothing that's really strange in terms of outliers. And you want a good mix of positive and negative residuals. So in other words, if if you think about this, you want to make sure that you got some values that are above the line of best fit and some values that are below. You want a good mix of that. The final thing that we kind of looked at with all of the linear regression information was you can sometimes run across a data set if you don't have a good residual plot, or if you look at the original, all of a sudden it might not look linear, so we can transform the data. If you'll notice, I put a note down here for you. Chances are, if you do interact with something like this, you're going to be given, you'll be given like the natural log of y. You'll be given the line of best fit, so maybe that's 4.62 plus 6.87x, where they've already done the transformation, and you're just going to be asked to do something in terms of making a prediction. So this is just a matter of be very careful with your algebra. And remember that in order to solve these things, you're going to have to use, e or base 10 to solve for y. So the two forms that we could see, an exponential model is when you took the log, or as you see below, the natural log. When you just do that to list 2 or our y list, and then a power transformation is when you take the log of y and x, or for us it would be the log of list 1 and list 2. So again, the most likely scenario you'll see here is that you're going to be given a transformed equation, and you're going to have to do something in terms of a prediction or maybe a residual, which again is a prediction, something like that. So a quick example, here's some data on shoe sizes and heights. So to create a quick scatter plot of this, so we'll put shoe size on the x and height on the y-axis, and so it's going to be shoes versus height. And what I'm going to do is just do a quick sketch. Obviously if we wanted a lot more detail, we could definitely do that in terms of labeling the axis and getting a better scale. But for us right now, I'll just get a quick feel for the look of the graph. And what we can see from that, that's a strong positive, and I'm going to go ahead and say linear relationship. So there's describing the data, so our quote-unquote version of SOX. Find the line of best fit. So that's where we're going to go to the linear regression function under the stat calculate. And our line of best fit, y hat equals 1.87 plus, read that a little bit wrong, 51.36 plus 1.87x. So the interpretations, again, slope for every 1 unit increase, or for every 1 increase in shoe size, for every increase in shoe size, and since it's positive, we know that height will increase by 1.87 inches. My y-intercept here tells me for a shoe size of 0, when x is 0, the predicted height, predicted height is 51.36 inches, and just that has no practical meaning. Okay. We can use our least squares regression line to make a prediction. So let's make a prediction. If we know someone's shoe size is 9.5, so 51.36 plus 1.87 times that size 9.5 foot is, so 51.36 plus 1.87 times 9.5, that prediction would be about 69.125 inches. We'll go 69 inches. Number 4, we're asked, what is the residual associated with 9.5 feet? Well, if you look back into your data, we do have one observation at 9.5 feet, or 9.5 size feet, and that was 70 inches tall. So to calculate the residual, obviously the prediction was 69 inches, right? So there's the predicted, and here's our observed up here. So again, a residual equals observed minus predicted. So for us, it is 70 minus 69. Oh, excuse me. Whoop. Switch that. The observed is 70. The predicted is 69. Is 1. So the last couple things here, we'll take a look at the residual plot. Again, if you've already run linear regression, once that's run, in your lists, you'll see a residual plot. So drop that into list 3, and then we're just going to plot list 1 versus list 3 and take a look at that residual. And I'll just do a quick sketch of it here. Quick sketch of it. So the residuals for shoe size here. We got there, here's one up there. Just giving it a quick sketch. I'm not being probably quite as detailed as I should be, but you can see there's not really a pattern to that. So that's a good looking residual plot, and it does look like a linear model is appropriate based off of that residual plot. The correlation, remember, in order to get the R and the R squared value, make sure your diagnostics are on, and the easiest way to do that is to go through your catalog. If you hit second 0, you can turn your diagnostics on. So our R value, our correlation is 0.926, which again kind of reaffirms this is a strong positive. Obviously R is positive, and it does, according to the graph, look linear. And then coefficient of determination, that's just R squared again, and if diagnostics are on, you get that information. And then to interpret that, that tells us that 86% of the variation in height is explained by the linear model of shoe size. The way that we have this set up, where shoe size was our x variable and height was our y.